So what's a neural network? Let's dive into this explainer and see how machines actually learn to see. You can easily read a sloppy number 3, right? But programming a computer to do that is comically hard.
Your brain instantly gets it. But a computer? It just stares at a massive, daunting grid of numbers. We start with 784 input neurons. That's literally one for every single pixel in a 28 by 28 image. Just think of a neuron as a bucket holding a number. It lights up when it's highly active. One layer lighting up triggers the next. Eventually, it lights up just one of 10 possible output digits. It's all about abstraction, really. We're breaking complex digits down into simple edges, little loops, and familiar shapes. So how do these layers actually talk to each other? Well, the secret is entirely in the math. We use weights. Positive weights crank up the relevant pixels, while negative weights just ignore all the background noise. Next, we calculate a weighted sum and pump it right through a sigmoid squishification function. Great word, right? Crucially, we add a bias. It's a threshold, making sure neurons only fire when a pattern actually matters. With just 2 tiny hidden layers of 16 neurons, we somehow end up with 13,000 parameters. That's 13,000 little dials to tweak. Imagine trying to set all of those by hand. Absolutely terrifying, right? Thankfully, code libraries use linear algebra, like matrix multiplication, to keep everything super simple and lightning fast. Fun fact for you, deep learning expert Leisha Lee points out that the sigmoid function is kinda old school now. Nowadays, modern networks mostly use a function called ReLU. Why? Because it's just way easier to train. Zooming out, this entire network is really just one giant, absurdly complicated mathematical function. Mind-blowing, isn't it? If reading a simple 3 takes 13,000 dials, what on earth does it take to actually understand reality?